Well, good morning, good afternoon, or good evening, depending on what time of day it is that you're watching this video. In this video lesson here, I'm going to go over with you how to find the volume of a region with known cross sections. If I thought we'd start this lesson out here with an old AP exam question. And this was on the width calculator part of the AP exam. So they gave us these two graphs here in region R. They said let R be the shaded region in the first quadrant enclosed by the graphs y equals e to the negative x squared, which is this one here, and y equals 1 minus cosine of x, okay, and the y-axis. So this shaded region here is what we're talking about. We want to find the area of that region. Okay, well that was one of the first lessons we did when we started talking about volume and area between two curves, was to find the area in between two curves. So the first thing we've got to do here is we've got to figure out what's this point of intersection right here. What's the value for x right there? Because to do part A here, we're going to integrate from 0 to whatever that is, and then we're going to take the function that's on top, the e to the negative x squared, and we're going to subtract the function that's below it, the 1 minus cosine of x. If we integrate e to the negative x squared, we get all the area all the way down to the x-axis. And then we'll integrate 1 minus cosine of x, we get the area in between this function and the x-axis. When we subtract it out, we get rid of that, and we just have the shaded area. So I'm going to grab my calculator, and I'm going to graph this. Okay, so let's see. Move this. Let's move this calculator down so we can see. There we go. All right, so I'm going to go to the menu. I'm going to go to graph. And I'm going to put in the e to the negative x squared and the y sub 1. So e raised to the negative x squared. And then the y sub 2, I'm going to put 1 minus cosine of x. Alright, now I get this weird looking stuff. All I really need to look at is like they did here. If I go to the viewing window, I'm going to look at x's from 0 to 1.5. And I'm going to do the same thing for my y's. I'm going to match it up to go from 0 to 1.5. That's what they have. Whoops. And this up there. Y minimum 0, maximum 1.5. Okay, we'll graph that again. Now the graph looks a lot like our graph here. Okay. So what I'm going to do is find this point of intersection. So I just go G-solve, intersect. And x is about 0.941. Okay, now I could round that off to 0.942 and probably get an answer that's good enough. Or what I could do is I can go back to the main menu. That number is in there for x. I'm going to store it, so it's a little arrow above, all clear. And I'm going to hit alpha x. I'm going to store it in A. Okay, now that number is in there for A. So on here, let's get rid of that. I'm just going to put in here 0.942. But when I enter this on my calculator, I'm going to go ahead and use that stored value. Okay. So I'm going to go to Option, over to Calculate, Integrate, and I'm going to do the e to the negative x squared, negative x squared, and I'm going to subtract a 1 minus cosine of x. And then we'll ask the calculator to do it from 0 to that value I stored in A. Whoops, I'm missing here. Oh, cosine of x. Self-sabotage, I forgot the x there. All right, so we get an answer of about 0.51 if I round that off. So this would be about 0.51 square units. And now in part B, they ask us to take this find the volume of the solid generated when we take that region R and revolve it about the x-axis. Okay, so we're going to bring it about the x-axis. So it's going to take this whole region and go around the x-axis and make a solid shape. Okay, so for part B, maybe I'll do it down here. Do it in purple again. And you know what, too? Well, yeah, we'll just keep going with this. The part B, we're just going to make circles. Right? So it's going to be pi times interval. We're still going to go from 0 to 0.942. But now we're going to have our big circles, or the radius of our big circles, minus the radius of our little circles. Right? In the big circles, the area is pi times the radius squared. The little circles, pi times the radius squared for the little circles. Now the big circles will have radii that go all the way from this function to the x-axis. Right, so that's basically just whatever y is here minus y is here. On the x-axis, y is 0, and up here, y is negative x squared. So all we're going to do, or e to the negative x squared, we're going to put e to the negative x squared in here. That's our big radii, and then our small radii just go from here to here. Right, what we want to subtract out is this region, so those radii are 1 minus cosine of x. So 1 minus cosine of x. Okay, hopefully you're seeing here that this is just like finding the area between two curves, but when we revolve it about the x-axis, we make circles, so we just square these things, these lines, these radii. Okay. So now it's just a matter of typing this in the calculator. I'm thinking I can just clear this, go back up here, come over here and put this e to the negative x squared in parentheses and square it, and do the same thing for the 1 minus, whoops, it's backwards, for the 1 minus cosine of x. Square that, and we get that the area is about 0.556 pi. Right, so about 0.556 pi. Now, if it seems weird to you to have pi with decimals, then by all means go ahead and take and multiply that by pi and just give an answer of 1.747. Right, or 1.747. Okay, so those are two things that we've gone over. Right, how to find the area between two curves, how to find the volume of a solid of revolution. The new thing we're going to do today, or in this video, is find volume given a cross-section, a known cross-section. So the region R is going to be the base of a solid. And for that solid, each cross-section perpendicular to the x-axis is going to be a square. We want to find the volume of that solid. Okay. So for part C, what we're going to have here, I'm going to erase out what I've written in here. Okay. We're going to have squares in here. And they're going to be, this is the base of the thing, and then the squares are going to come up off the page. Let's see if I can draw a better square than that. Maybe I'll draw them like that. They're coming up off the paper. That's the base of the figure, and then the squares come up off like this. And I'm not the greatest three-dimensional drawer, but picture these squares coming up off the screen to make a solid figure. And maybe picture something like this. I found this on the World Wide Web. Here's something that had a circular base and it had triangles coming off to make volume. And here's something that had an elliptical base, and then we had rectangles coming up off of it that made it have volume. Okay. That's what's going on here, but we're having squares. Okay, so they're perpendicular to the x-axis, so we want to find the area of one of these squares and then integrate from 0 to that 0.942. Right? At this point right here, x was 0.942. Yeah, better double check that. What do we have in here for our a? Yeah, 0.942, I didn't forget. Okay, so the reason why we integrate from here to here is because if we get the area of one square, then we integrate from 0 to 0.942, it adds up all the areas of all the squares and gives us the volume, solid volume. Just like for part B here, we found the area of the circles and we integrated it, added them all together to give us volume. We're going to do the same thing. So for part C, we're still going to integrate from 0 to 0.942. Okay, but now we're no longer going to have a pi in front because we're not finding the area of circles. Before, the only reason we had pi is because we were finding the area of circles, and the area of a circle is pi times the radius squared. So there's no pi involved with these. Okay, now all we got to do is figure out what's the area of one square and then integrate it with respect to x. So I'm going to go back up here and look at this. If I draw a line from the top curve to the bottom curve, right, that's the side of one of my squares. So maybe over here I'll draw one of these squares. And anytime I draw a line from here to here, the length of that line is just e to the negative x squared minus 1 minus cosine. Right, this is e to the negative x squared minus 1 minus cosine of x. That's side of a square. Right, the area of a square is just one of the sides squared. So I'll just come down here and I'll put in here e to the negative x squared minus 1 minus cosine of x. And if I square that, that gives me the area of one square. And then I integrate from 0 to 0.942. That adds up the area of every square and gives me the volume of this solid figure. So I'm going to go ahead and let the calculator do that for me. All right, so I'm going to integrate, and then in parentheses I'll put e, whoops, not natural log, I want e to the negative x squared. Then I'm going to subtract 1 minus cosine of x. I'm going to square that entire thing and then do it from 0 to that 0.942, which we stored in A. And we do that, we get the area is about 0.461 cubic units. So 0.461. Hey guys, that problem right there is off a previous year's AP exam. It was a free response question. It was 3 points for each thing, so it was 9 points out of 108. So it was a decent part of the test. Okay? Every year on the AB AP exam, there'll be something like this. Okay? Usually, a lot of times on the BC as well, but not every year. It's guaranteed to be on there every year on the AB exam. All right, so what we're going to do here is a couple more examples. We're given some base, that's a circle, an ellipse, a square, some weird shape or some shape, and we've got cross sections that we know are coming up off of it. We're going to figure out how to find the volume of that figure. Okay. So this is finding volume with known cross sections. So here's another example. We're going to find the volume of S. The base of S is an elliptical region with boundary curves 9x squared plus 4y squared equals 36. And then known cross sections perpendicular to the x-axis are isosceles right triangles with the hypotenuse in the base. All right, so my suggestion is first thing, sketch the base of your region. Okay, so it's an isosceles, or it's an elliptical region, right? And then the cross sections are isosceles right triangles. All right, we could go through and we could put this in standard form and graph it, or we know an ellipse is just, a stretched out circle. If I put 0 in for x, 4y squared would be 36, so it would go up to 9, down to negative 9. If I put 0 in for y, it would be stretched left 4 and right 4 because 9x squared would equal 36. Actually, x squared would equal 4, so it would be plus or minus 2. And if I put 0 in for x squared, y squared would be 9, so it would be plus or minus 3. So actually we've got an ellipse that maybe does something like this. Again, I'm not the greatest at drawing these things, but this point right here would be 2, 0, and this point over here would be negative 2, 0. Right? If we put 0 in for y, we get 9x squared is 36. So x squared would be 4, so x would be plus or minus 2. Right? If we do the same thing with the x, if I put 0 in for x, this goes away and I get 4y squared is 36, so y squared is 9. So this goes up 3 to 0, 3, and it goes down 3 to 0, negative 3. All right, now they're telling me cross sections are perpendicular to the x-axis. All right, as soon as I see that they're perpendicular to the x-axis, I know I want to do everything in terms of x, because my triangles are going to look like this. My hypotenuse is going to be here, and then they're going to be right triangles. I should draw, well, we want that to be a right angle. Let's see. Something about like that, maybe. Right, and that's a right angle. Okay, because the hypotenuse is on the base. So we're going to have a bunch of these triangles that are on here, and they're coming out here, right, to give this thing its solid shape. And they go from one side to the other side. And if we could find the area of one, then we integrate from negative 2 to 2, and it adds up the area of every single one of them and gives us the volume. So I know I'm going to integrate from negative 2 to 2. And I want to do it in terms of x. I want to do how to find the area of one of these triangles, and I'm going to integrate that in terms of x. So what I'm going to do is over here, so I'm going to draw one of these triangles. And maybe I'm going to draw it like this because it's easier on me to draw it like that. Okay. So that's the right angle, so this is the hypotenuse. The hypotenuse is this part right here. Okay, if I was to take my triangle here and turn it around, it actually looks like that. Right? It matches up with these right here. And I've just got an infinite amount of triangles going from negative 2 to 2 right there. So we've got to try to figure out something about this triangle and then get the area in terms of x. So one thing a lot of people notice right away is if we had a triangle right here on the y-axis, the hypotenuse would be 6 because we went up 3 and down 3, or from negative 3 to 3 is 6. Try to use that same reasoning. Let's say we were right here. Right? I drew a triangle with the hypotenuse right there. This point has got some x and some y. This point down here should have the same x and the opposite of y. So from here to here it would just be y plus y. The hypotenuse is going to be 2y. Now, if I take that and I put it back like this again, because I like looking at it like this. All right, I'm going to call this the base of the triangle and this the height of the triangle. Right? In a right triangle, the legs are the base and the height. Now, it said it was an isosceles right triangle. So that tells me these two sides are the same. It tells me the base equals the height. So I'm just going to come here, and I'm going to say the height is the same as the base. I'm going to call that b. Now, the area of a triangle is 1/2 base times height. So it's 1/2 b times b, or 1/2 b squared. Okay. Now, I need to get this in terms of x. Right off the top of my head, I don't see a way to do that, but I do know the Pythagorean theorem. I do know that b squared plus b squared should equal quantity to y squared. So 2b squared should equal 4y squared. Divide by 2, and b squared should be 2y squared. So I'm making some progress now. I'm going to come over here, and for the area, I'm going to replace b squared with 2y squared. So now I've got the area in terms of y. I just need to get it in terms of x. Now, if I go back to the original problem, look at this right here. They gave us a relationship between x and y. 9x squared plus 4y squared equals 36. So in our area formula here, we've got y squared. Let's just solve this for y squared. All right, so 4y squared would equal 36 minus 9x squared. All right, and then I'll divide everything by 4. And y squared is going to equal 9 minus 9/4 x squared. So I can come down here to my area formula, and I can replace y squared with 9 minus 1/4 x squared. All right, because that's what y squared equals. So that would be the area of one triangle, 9 minus 1/4 x squared. That's what I'm going to put in here. 9 minus 1/4 x squared. That's how we find the area of one triangle in terms of x. And then when we integrate from -2 to 2, it adds up the area of every one of those triangles and gives us the solid volume, the volume of the solid. Now, when I come over here, I'm working without a calculator. Whenever I can make things easier on myself, I should. I noticed 9 minus 1/4 x squared is an even function. So I'm going from -2 to 2. So instead, I'm going to go from 0 to 2 and double the answer. So now I got 2 times antiderivative of 9 with respect to x is 9x minus antiderivative of 1/4 x squared. Well, antiderivative of x squared would be x cubed over 3. So this is going to be 1 over 12 x cubed. Right, so I can think of x to the squared over 4. So I add 1, divide by 3. Now I'm doing this from 0 to 2. All right. Now when I'm looking at this, and I just happen to glance right here, and I glance right here, guys, silly, careless mistake. It says 9 minus 9/4 x squared. Right, I got 9 minus 1/4 x squared. This should have had a 9 up here. Right? It's 9/4 x squared. When I wrote it down here, I should have had 9/4 x squared. Okay, so now when I integrate this, I get x cubed over 3, so I get 9 over 12. And that could make a huge difference in the answer here. Now I plug 2 in there, and 9 times 2 is going to give me 18, minus, plug 2 in here and I get 8, times 9 is 72, divided by 12 is 6. And look at that, 18 minus 6 is 12, times 2 is 24. So the volume of this solid figure is 24 cubic units. And now, you guys, the calculus part wasn't too difficult, right? Integrating this was not hard. It's the geometry you're going to have to remember to do these things, finding the area of different shapes and graphing them that's going to make these more involved. Okay. So let's try another example. Well, right. Let's find the volume of S. If the base of S is this parabolic region, and now they're giving us some set notation. They're saying it's the set of points such that x squared is less than or equal to y, which is less than or equal to 1. And this time cross sections perpendicular to the y-axis are equilateral triangles. All right, so we're going perpendicular to the y-axis. So as soon as I see that, I know I want to do everything in terms of y. And now this notation I'm going to break down a little bit. They're basically telling me my functions are y equals x squared and y equals 1. Okay, so if I picture that region, y equals 1 is just a line like this, and then y equals x squared is a parabola that does something like this. So there's y equals x squared and y equals 1. We want all the points where y is greater than x squared, so above x squared, and below y equals 1. So we're looking at this region in here. Maybe I'll highlight that. in yellow here. Right? This is the region we're talking about. Now, in that region, we have equilateral triangles that are perpendicular to the y-axis. So maybe I'll draw them in blue here. We have triangles that look like this, right, that are coming up off the page to give this, whoops, doesn't go up there. They're only in the yellow region here, right? They come off the page to give this region of volume. Okay. So we want to do everything in terms of y. So over here I already know I'm going to integrate from 0 to 1 because that's where we go in terms of y, 0 to 1. Now I got to figure out what's the area of one of these triangles. So maybe I'll draw just one triangle right here. Okay, now it's equilateral, so I know all the sides are the same. I got to get some bearing here, something I know about one of the sides. And I think it's going to be this side right here. If I do this again, this side right here is this. It's from here to here. And now, where these things intersect, this point right here is the point 1, 1. And this point over here is the point negative 1, 1. So this red line has a length of 2. Because we went from negative 1 to 1, right? I pick different areas, the lengths are different. They get smaller as we go down, bigger as we go up. But they always have this in common. This point on the right would have an x and a y, and then the one on the left would have the opposite of that x and a y. So I know from here to here is just 2x. We're going from negative x to x. So I know this side is 2x. If it's an equilateral triangle, then all the sides are 2x. Okay, now I can do, well, I'm going to write over here the area of a triangle. Right? The area of a triangle is 1/2 the base, which in this case the base is 2x, times the height. So I got to find the height. And the height is going to be right here. Right? That's going to be the height. Now, this is nice when we draw an altitude in an equilateral triangle. Not only does it make a right angle with the opposite side, but it bisects the angle up here and it bisects the opposite side. So this side now, from here to here is x, and from here to here is x. Now, if we bisected this angle, all these angles were 60 degrees because it's equilateral, they're all the same. So now this one's 30 degrees. So now we've got our 30, 60, 90 triangle. We could use our special ratio. Right? We know in a 30, 60, 90 triangle, this goes square root of 3, 2, 1. And look what we have here. We have 2x right here, 1x right here. So this side should be square root of 3x. So I know my height is the square root of 3x. Okay, now let's say we didn't remember our ratios there. We're still in luck. This is a right triangle, and we could use the Pythagorean theorem. H squared plus x squared should equal 2x squared. Right? The legs, sum of the legs squared should equal the hypotenuse squared. So this would be 4x squared. Bring this x squared over and subtract it, and we get h squared is 3x squared. Take the square root of both sides, and h would be the square root of 3 times the square root of x squared, which is x, or square root of 3x. So now we've got the area of one of these triangles is just going to be the square root of 3 times x squared. Okay, now, we've got the area in terms of x. We need it in terms of y. Because the triangles don't go from left to right. They go from bottom to top. They go from below to up. So we need it in terms of y. So let's see. Here's a relationship right here between x squared and y. Y equals x squared. So I can come right down to here and get the area in terms of y. All I do is I replace x squared with y. And there's our area in terms of y. So the area of one triangle is the square root of 3y, and then we integrate that with respect to y. Antiderivative of this would be square root of 3y squared over 2. We'll do it from 0 to 1. Plug 1 in there, we get square root of 3 over 2. Plug 0 in there, we get 0. So the area is the square root of 3 over 2. You guys, it's that easy. Look how easy the calculus was. It was the geometry that we had to do to make the calculus easy. Or trigonometry, whichever we used. Okay? So we just got to work these through. And I got a couple more examples. Let's try a couple more examples. Okay, here's one I found in an old Larson, Hostetler, and Edwards book. And something's going on here with my slate. So let's see. See if I can get this thing working. All right, now we're back up in there. All right, this one says find the volumes of the solids whose bases are bounded by the graphs of y equals x plus 1 and y equals x squared minus 1 with the indicated cross sections taken perpendicular to the x-axis. All right, perpendicular to the x-axis, so we want to do everything in terms of x. Okay, we need to see what does this region, what's the base of these regions look like. So again, I'm a big proponent. Sketch these graphs. Right, x plus 1 would be something like this. All right, this would be the graph of y equals x plus 1. And then x squared minus 1 would just do something like this. And I think before I do those, maybe I'll set these two equations equal. Where does x squared minus 1 equal x plus 1? So I bring everything over here and I'll get x squared minus x minus 2 is 0. So this factors to x minus 2 times x plus 1 is 0. So x could be negative 1 or 2. All right, now negative 1, when x is negative 1 plus 1, that's going to be 0. So they intersect right there. Then when x is 2, we're going to get 3. So maybe about right there. So they intersect here when x is 1, negative 1. Then over here when x is 2. So the parabola does something like this. So there's the parabola is y equals x squared minus 1. So this region right here is the base of our solid figures that we're going to work with. And let's see. I'm going to snap a little picture of this. And we're going to do it twice. So if I write on it, it's doing that to me again. Let's try this. Let's see if I can do it without getting that little line through the middle of it. Well, we'll give it one more shot. If not, we'll just monitor and adjust here with some other things. Now look at that. That's going to be worse. Oh, look at that. Maybe it wasn't. All right, so first here, I'll do it if the cross sections are squares. Okay, let's say in here we've got squares that run from the top region to the bottom region. They look something like that, and they come up off the screen to give this thing volume. Okay, so we're going to do it in terms of x. So in terms of x, I'll step down here, we're going to integrate from negative 1 to 2. Okay. Then I got to figure out what's the area of one of these squares. Well, if I go from here to here, that's the side of the square. I'm just going from the line to the parabola. So it's basically the line, which is x plus 1, minus the parabola, which was x squared plus 1. Oops, x squared minus 1. So let's see, that would be negative x squared plus x plus 2. Okay, that would be the length of a side. Well, the area of a square is just a length of one side squared. So then all we got to do here is do negative x squared plus x plus 2, and then square that and integrate it with respect to x. Now, I could square this out, right? Integrating stuff, there's just a lot of tedious work. Save ourselves some time here. The new skill we're working on here is setting these things up. I'll just integrate it in the calculator. So we got negative x squared plus x plus 2. That's the side of a square, so I square it to get the area of the square. Then I integrate it from negative 1 to 2. Oops, what did I miss? Oh, negative 1, I missed the 1. That's pretty nice. It puts the cursor right there. It shows me. So look at that, 81 over 10. So this volume of this figure would be 81 over 10, or 8.1 cubic units. Now this next one says cross sections are rectangles with a height of 1. Rectangles. So that means instead of squares here, we've got rectangles that only have a height of 1. So they're like that. Right, they're not coming up off the picture a long ways. They're just 1. Well, find the area of one of these rectangles, and let's set this up here. We're still going to integrate from negative 1 to 2, but now the area of a rectangle would just be the area of one of the sides, and we already know the side going from the line, whoops, because I didn't make these things go all the way down here either. That's no good. Okay, it's the line from the line to the parabola. So one of the sides we know is already the negative x squared plus x plus 2. And then with a rectangle, it's length times width, or base times height. The height is just 1, right? They told us the height is 1. So we just do that. So basically, we're going to take this same integral, but it looks like we're going to take away the squared. And we'll get a volume of 9/2. Okay, now, if they would have said the height was 2, we'd have to multiply this by 2. Or if the height was 3, we'd have to multiply it by 3. We'll say 9/2. So this turned out to be 9/2 cubic units. Right, again, if the height was 7, we would have had to do this times 7. Right, when it's 1, it's nice. All right, how about this right here? This is off of previous year's AP exam. It was one of the multiple choice questions. It was on both tests, the Calc 1 and the Calc 2. And it was a without calculator question. So the base of a solid is the region bounded by the x-axis, and the graph of y equals square root of 1 minus x squared. Then for the solid, each cross-section perpendicular to the x-axis is square. We want to find the volume of the solid. All right, so this seems like it's a lot like what we just did. All right, so again, I would sketch this. What does this look like? Well, 1 minus x squared, if I'm not mistaken, is just top half of a circle that goes from negative 1 to 1. Right, because if we squared both sides, we get y squared equals 1 minus x squared. Bring the x squared over, we get x squared plus y squared is 1. It's just a circle centered at the origin with the radius of 1. We've got just the positive square root part, so it's just the top part of it. Okay, now, cross sections, that's the base of it, and cross sections perpendicular to the x-axis are squares. So that means we've got squares coming up off the page to give it volume. All right, so we're going to integrate from negative 1 to 1. Then we have to just figure out what's the area of one of those squares. Well, the area of a square is just one of the sides squared. So if we think about it from here to here is just whatever y is on this curve minus 0. And on the curve, y is the square root of 1 minus x squared. So the length of one of the sides of these squares is the square root of 1 minus x squared. You guys look at this. We square this, and we just get 1 minus x squared. Right? Because the square cancels the square root. Now again, I'm looking at this. This is an even function. So I'm going to go from 0 to 1 and double the answer. Now you don't really have to do this. It's not that complicated, but this just cuts my work in half. So I get 2 times. Integrate this, I'll get x minus x cubed over 3, or 1/3 x cubed. Do it from 0 to 1. So put 1 in there, I get 1 minus 1/3. Put 0 in there, I'm going to get 0. So 1 minus 1/3 is 2/3, times 2 is 4/3. So look at that. The answer is 4/3. You guys think about it. People say the AP exam is difficult. Right? It really isn't. They're going to put stuff like this on here that if you know what you're doing, it's fairly simple. They're going to put traps in there, right? 2/3 is one of the answers. That's what I would have got if I didn't double it when I went 0 to 1. They're also going to put 4 pi over 3 in there. Because sometimes, for some reason, people want to put the pi in front of it. Remember, you only do pi if you're revolving about a line, because then you're making circles. We weren't making circles here, we're making squares. Okay. So this, guys, you can do this. If you need more practice, go on the Google machine, look up, just type in volumes with known cross sections, practice, and you'll find plenty of places with problems with the answers to practice. Right? Ask me for help. Ask your friends for help. Do what it takes to figure this out so that you can do it. And guys, most of all, I'll leave you this parting advice to always endeavor to persevere.